Okay, so we are actually going to start looking at how we can apply some of these projection methods to specific things. So in other words, we have these K spaces and L spaces. To be able to apply this, we need to figure out what K and L should be. So in this video, we're going to look at 3 different methods where K and L are going to be one-dimensional spaces. But I want to just remind you a little bit about what we're doing. We're going to look at vectors, iterative methods of the form where the updated vector is going to be of the form x naught plus delta. Delta is going to lie in some subspace K. And since delta is lying in some subspace K, that means, and if we're assuming K has dimension m, we need to come up with m equations to tell us what delta is. And hopefully these equations that we come up with are going to give us better approximations. Are going to be such that x tilde will be a better approximation. So these conditions come in the form of orthogonality. So we want, let me write it differently. We want b minus ax tilde to be orthogonal to some subspace L that has the same dimension as K. This gives us m equations. Okay, and we've looked at 2 different situations so far. One, we've looked at the situation where L is just equal to K. And 2, we've looked at the situation where L is equal to A times K. In other words, for every vector in K, do A times that vector, and then if you do that for all of the vectors in K, this gives you L. Okay, so I've mentioned this in previous videos, but what I'm about to describe is going to be very important for the methods that we look at tonight. Well, it's tonight now for me. I don't know when you guys are watching this, but for the methods that we look at in this video, what I'm about to say is important. Even though I've said it before, it needs to be said again. So let's analyze method 1. So what we want is we want b minus a x delta to be orthogonal to K, and delta is going to lie in our subspace K. So if we unpack this a little bit, x tilde is x naught plus delta. So we can write this as b minus a x naught minus a delta we want this to be orthogonal to K, and again delta is in K. Okay, what does this orthogonality mean? What does this orthogonality mean? Well, it means we want this difference to be the inner product of this difference with any vector in K to be equal to 0. So what we want is we want b minus ax0 minus a delta. We want this to be equal to 0 for all w in K. But let me remind you, what is b? Well, if x star is the actual solution, then b is equal to ax star. So I can rewrite this in the following way. I can write b as ax star, where x star is a solution. Then I'm going to have minus ax0 minus a delta w is equal to 0. And then I can rewrite this in the following way. I can write this as a, look, there's an a on each one of these terms, x star minus x naught minus delta w is equal to 0 for all w in K. But all this is right here, this is just the inner product defined by A if A is a symmetric positive definite matrix. Okay, so in other words, what this is saying, it's saying that delta is the A orthogonal projections. When I say A orthogonal projection, I mean orthogonal relative to the inner product generated by A. Delta is the A orthogonal projection of x star minus x naught onto K. So let me record that over here. So let me see if I can find a nice color to use that I don't have on the board already. Okay. So in this case, delta is equal to the A orthogonal projection of the error x star minus x star minus x naught onto K. And here, for this to make sense, really, A needs to be symmetric, positive, definite. Otherwise, the reason we need that, the theory requires that it works, requires that, but for us to be able to define an inner product with A needs to be symmetric, positive, definite. Okay. Now we can do a similar analysis for method 2 here. So what we want is I don't know why I started with A. We want B minus AX tilde. This one is actually a little bit easier to think about, even though L looks a little more complicated. This one seems more natural, like in terms of orthogonal projections, but this one somehow I think is a little bit easier to understand. Anyways, B minus AX tilde to be orthogonal to this space AK. And again, we want delta to be in K. Now, delta doesn't appear explicitly in that formula there, but that's okay because we know x tilde is equal to x naught plus delta. So we can write this as B. This is very similar to what we did in the previous one. B minus AX naught minus a delta to be orthogonal to AK. So now what this is saying that one more thing. B minus AX naught, remember that is the residual. This is R naught minus a delta is orthogonal to AK. Okay, so in this case, A delta is the orthogonal projection, just the standard Euclidean orthogonal projection. Orthogonal projection of R naught onto the subspace AK. Okay, so A delta is the orthogonal projection of the residual onto AK. So let me say that down here. And essentially what we're going to find out here is we don't need many requirements on A. Okay, so A delta is the orthogonal projection, and if I don't specify the inner product, it just means the standard one. The orthogonal projection of the residual R naught onto the subspace AK. Okay. All right, and I'm going to remind you one other thing. We're going to be dealing with one-dimensional projections here. In other words, K and L are going to be one-dimensional. And so in other words, they're just spanned by one vector. Okay, so let me just remind you of this. If K is just the linear span of one vector, this L is not this L. This is the fancy linear span L. So if K is just the linear span of one vector, in other words, this is this all C times V such that C is a real number or complex number, but for us we're dealing with real numbers. Then the projection projection, and this is going to be under any inner product. This formula will work for whatever inner product we're dealing with. The projection of a vector x onto k is simply v x divided by the inner product of v with v times v. Okay, and again, this is true no matter what inner product we're dealing with. If it's the A projection or the standard projection, this is the formula, okay, but the inner product could mean different things, all right? Okay, so keep that in mind. This is just like a very standard thing that you learned a long time ago, like in a Calc 3 class probably. Or actually, I think here we might even do it in our Calc 1 class. I don't remember. Okay. So we're going to look at three different algorithms. We're going to look at three different algorithms for different choices of K and L. Maybe I would say not three different algorithms, maybe 2.5 different algorithms. You'll see what I mean by that in a minute. Okay, so the format that I'm going to do this in is I'm going to write down what the algorithm is, okay, and then I'm going to say this algorithm corresponds to this choice of K and this choice of L, and then I'm going to show you why that algorithm actually does correspond to a certain choice of K and a certain choice of L, because it's not, like the formulas are not completely clear right away. There's like a computation that you have to do. So the first one we're going to look at is steepest descent. So this is based off, you might have heard this before, this is based off of basically multivariable calculus. We have some function that we want to minimize, or this is in some sense based off of that, or it's the same as that. We have some function that we want to minimize, some function of several variables that we want to minimize, a scalar valued function of several variables that we want to minimize. You might remember from your Calc 1 class, or your Calc 3 class, that the gradient is a vector, and it's going to give you the direction of the biggest increase, and the negative gradient is going to be the direction of biggest decrease. So we're going to look, the way that we can formulate this, and I'll explain it in just a minute, is we want to look at how we can, we're going to go in the direction of biggest decrease. The function that we want to minimize is the error function, and we want to look at the direction of biggest decrease. Okay, anyways, so without further ado, like I said, this is the steepest descent algorithm. Okay, so if you sort of imagine being on a surface, let's say you want to get down, you're on a mountain, you want to get down as fast as you can, you're going to look right around you and figure out the steepest possible direction to go in, and you're going to go down that direction. Okay, that's why it's called steepest descent. Okay, so what it says is the following: R is going to be equal to B minus AX. I'm going to say R is equal to B minus AX naught. Alpha is going to be equal to the standard inner product of R with R divided by AR R, and then U X tilde is going to be equal to X naught plus alpha times R. Okay, so R is the residual. Alpha looks like we have some sort of projection thing going on, which is reasonable because we're talking about projection methods, and then X tilde is the update. So what we're saying here basically is that this is the delta. Okay, so what is this? This algorithm corresponds to the situation in which K is equal to the residual vector. Let me be more precise. K is the linear span of the residual vector B minus AX naught, and that's also going to be equal to L. So in other words, we are in this setting right here. So alpha R, that is delta, it is the A orthogonal projection. That's what I need to show. That is the A orthogonal projection of X star minus X naught onto k. Okay, so in other words, what I'm going to do is I'm going to say, okay, let's forget about, we have this here, let's just forget about it for a minute. I'm going to come up with what the formulas should be in the setting where k is a linear span of r, where r, as always, is equal to b minus ax, and L is equal to k. Okay, then we'll see that the formulas are the same. Okay, wonderful. So how is this going to look? So delta is the A orthogonal projection of x star minus x naught onto k. Okay, so let's just write out what that is. Delta is equal to the A orthogonal projection of x star minus x onto k. Okay, so this is going to be x star minus x naught. Okay, k is a one-dimensional subspace, so it's just going to be that formula that I gave before, and I'm going to put an a here, letting us know that it is the A inner product divided by r in the A inner product times r. Okay, good. So let's unpack what this means. Remember what the A inner product is. The A inner product is just A times this is just, well, it's this. Okay, so this is the standard inner product, the Euclidean inner product, and we're going to divide by AR, R, and then we're still multiplying by R. Okay. Well, what is AX star minus X naught? Well, AX star is B. So this is B minus AX naught. That first term is B minus AX naught divided by R, and then AR, R like that, and there we have it. So that's what delta is. So x naught, x tilde, is going to be x naught plus delta. Okay, but notice B minus AX naught, that's just R. So this is R. Over here, R is equal to B minus AX naught. I guess to be consistent with the subscripts, I'll put that there as well. Okay, so this is inner product of R with R over the inner product of AR with R times R. Okay, when we come over here, we've got the R. This right here, this alpha, is exactly the coefficient that we have there. Okay, so what it tells us is that the steepest descent algorithm is this projection algorithm that we've seen before in the specific case where k is equal to the linear span of the residual vector and and L is equal to k. Okay. So I'm going to tell you, but not prove to you, a theorem about the convergence of this method. But actually, before I do that, let me point out that this is what we're doing here. We're trying to minimize the function. If we have f of x, we're trying to minimize x minus ax star, where x star is the actual solution. We're trying to minimize this in the A norm. That's what we're doing. Remember, we're trying to minimize the error between the current guess and the solution in the A norm. That's what we're doing in this setting right here. Okay, now if you write out what this is just A times x minus x star, x minus x star. And if you take the gradient of this, you're going to see that it is minus a multiple of r. Okay, now I will let you look online about how you can take the gradient of something like this. Let me just point out, if you have the gradient of a dot product, which is exactly what we have here. Okay, if as long as you define things in the way that they should be defined, basically it's what you need to do to make the stuff work. This is going to be equal, there's sort of a product rule, the gradient of f, this will be a matrix, times g, plus the gradient of g, and again this is a matrix, times f. What is this matrix? Well, let me just put down here. The ij entry of the gradient of f is going to be the partial derivative of the ith entry of f with respect to the jth variable. And so what's going to happen is that the gradient of a times x is just going to end up being a. Okay, so that is the hint that you can do to show this. Anyways, that's just explaining why we call this steepest descent and the connection to the gradient. The gradient is the steepest descent method. Okay. So, here's a theorem. Again, I'm not going to prove it, but I'm going to say it. Maybe if I have another more theoretical week, I will prove this, but for now I'm just going to say it, and then we'll have to apply it. Okay. So the A norms satisfy the following. The error, that is the error of the kth plus 1 iterate. In other words, the error measured in the A norm. So in other words, this is the distance between the actual solution and our k plus 1th iteration in the A norm. This is less than the following. One second, let me make sure that I have this correctly. Yes, this is less than lambda capital M, that is the biggest eigenvalue of A. Remember A, we're assuming A is a symmetric positive definite matrix, so all of the eigenvalues are positive. So lambda M is the biggest all of the eigenvalues are real and positive. So lambda M is the biggest eigenvalue, minus lambda little m, that's the smallest eigenvalue, divided by lambda big M, the biggest eigenvalue, plus lambda little m, the smallest eigenvalue, times the error of the previous step. Okay. Now, one thing that's helpful, if C is the condition number of a matrix, the condition number of the matrix is typically defined as just being the biggest eigenvalue divided by the smallest eigenvalue. So lambda m divided by lambda big M divided by lambda little m. We can write this as C minus 1 over C plus 1. And this is helpful because oftentimes we will sort of work in the framework of condition numbers. The bigger the condition number, the worse. Basically, the worse the matrix is. So notice the condition number is always going to be greater than or equal to 1 because this is greater than or equal to this by definition. And so now what's going to happen as C goes to infinity, in other words, as the condition gets bigger and bigger and bigger, this is going to go to 1. And we want this is going to be like our convergence rate. We want this to be as close to 0 as possible. So as C gets bigger, this goes to 1, and the convergence gets worse. Okay, great. This was the steepest descent algorithm. It was the steepest descent algorithm, and it was based on minimizing the error between the current solution and the actual solution. Well, the next method is going to be based on this, and it's called the minimal residual. Because remember what we're doing, what we're minimizing here, we're trying to minimize the residual in the normal, in the standard Euclidean norm. Okay, so here's what the algorithm, I'm going to do the same thing. So this is minimal residual. Minimal residual, or minimum residual. R is going to be equal to B minus AX naught. Alpha is going to be ARR divided by, and this, since I'm not writing anything right there, these are just the standard Euclidean inner products. And then X tilde is going to be equal to X naught plus alpha R. Okay. There's the algorithm, minimum residual. Okay, so now in this case, it's going to be similar to what we had before. K is going to be the linear span of R, and L is going to be equal to A times K, or the linear span of A times R. So we're in this setting here. And so this tells us A delta is the orthogonal projection of R naught, or R. I'm calling this R, even though maybe it would be more consistent to call it R naught. Okay. It's the A delta is the orthogonal projection of R, or R naught, whatever you want to call it, onto AK. Okay, so that's what A delta is. So I don't have an expression for delta. So in other words, this right here is like my delta. In the previous example, we knew that delta was something, so I could just write delta equals something. But in this case, we know A delta is something. So that's what I'm going to write. I'm going to write A delta. What is A delta equal to? Well, it's the orthogonal projection of R onto AK. It's the orthogonal projection of R onto AK. What is AK? It's this right here. Again, it's a one-dimensional subspace. Okay, so we're going to look at R, which is B, well, I don't need to write that out. R times AR divided by AR, and then times AR, okay? We're just doing the one-dimensional projection formula that we saw at the beginning, where that vector is AR. Okay, but now notice what can happen. This is just a scalar. This is just a scalar, so I can move the A here. And this is equal to A times R minus RAR over AR, and now we're doing this with R. Okay, so clearly, if A is invertible, then the only solution is delta is equal to this part right here. But even if A isn't invertible, a solution to this is delta. Let me write a better delta than that. Delta is equal, okay, so R comma AR, this is a real inner product, so this is just AR comma R divided by AR times R. And that's exactly the formula we have here. ARR over AR is exactly what we have here. Okay. And so this tells us that yes, the algorithm given by these formulas is exactly the algorithm that we get when K is equal to the linear span of R and L is equal to A times K. Okay, so here's a theorem. I wrote down the number in my notes. In the book, this is theorem 5.3. And again, I'm going to tell it, but I'm not going to give it. So this says, let A be positive definite, not necessarily symmetric. So positive definite. Again, it's not necessarily symmetric. Okay, so let A be a positive definite matrix, and let mu be the smallest eigenvalue. Let mu be the smallest eigenvalue of A plus A transpose divided by 2. And let sigma be equal to the norm of A in the norm induced by the 2 norm. Okay, then we have the following. The residual in the k plus 1th step measured in the 2 norm is less than or equal to 1 minus mu squared divided by sigma squared to the 1/2. And then, of course, times the 2 norm of the residual in the previous step. Okay, now notice sort of, in a certain sense, we might think about sigma as being something like it's not, but we can think about it as being the spectral radius or the biggest eigenvalue. And so what we have here is like 1 over the condition number, or 1 over the condition number squared. So in other words, as the condition number gets bigger, 1 over the condition number gets smaller, and 1 minus that gets closer and closer to 1. So the bigger the condition number, the slower the convergence rate. Okay, awesome. Now we're going to move on to the last method that I want to discuss. And this is kind of going to be a hybrid of what we've already seen. And you'll see what I mean by that. Hybrid doesn't really seem like it should make sense because it's either one or the other here. But you'll see what I mean. You'll see what I mean. Just trust me. Or don't and wait. Okay, so this is called residual norm. I can never keep track of what all of these methods are called. The residual norm steepest descent. Okay, so what is this algorithm? R, as always, is going to be equal to B minus AX naught. Now our alpha is going to be equal, sorry, I need one other step here. R is equal to B minus AX naught. V is equal to A transpose R. Alpha is equal to the square of the V norm, the square of the norm of V in the 2 norm, divided by the square of AV, and then X tilde is going to be X naught plus alpha times V. Okay. That is the algorithm. And so again, what we're saying is that this is our delta, but I haven't told you what the spaces are. Okay, in this case, K is going to be the space spanned by V and remember what V is, it's A transpose R. And L is going to be equal to A times K. So in other words, it's going to be the space spanned by A transpose R. Okay, so now we are in this setting here. So once again, we know that A delta is the orthogonal projection of R naught onto AK. So, sorry, I got a text message that distracted me. Anyways, where was I? A delta is the orthogonal projection of R onto AK. So let's write out what that is. So again, like the last example, we don't have a formula for delta. We have a formula for A delta. And we know A delta is the projection of R onto AK. So it's going to be, what is AK? It's A transpose R, and then times R over here, divided by A transpose R, A transpose R, and then times A transpose R. Again, we are projecting onto L. L is A times K. In other words, it's the linear span of A transpose R. And this is just the one-dimensional formula. Okay, now what we're going to do, well, these are just the normal inner products, so the transpose could move over there. So we're going to have A transpose R, A transpose R, divided by, okay, I'm running out of room here, so I'm going to have to erase some stuff. A transpose R, that's just V. So I can write this as V. A transpose R, well, A transpose R, again, is equal to V, so I can write this as AV. Okay, and now what I can do is this is a scalar, so as I did before, I can put the A over here. So I can put the A like that. And then over here, I'm going to have the A transpose R, which is V. So A delta is equal to A times this. So if I choose delta to be that right there, then I'll have what I need. And that right there is exactly what you get, alpha times V, with this formula right here. Remember, the inner product of a vector with itself is just the square of the norm of that vector. Okay, so these are three methods. These are three methods that you can see are pretty easy to implement, and you can implement them right now if you want. Okay, but that's going to be it for this video. And now, after this, we're going to start looking at the Krylov methods, which we really get into some exciting stuff there.